Slide that I was looking for the other day this is the Alcoa book called From Monopoly to Competition, and it's a book about Alcoa that wasn't written by Alcoa. It's written by some guy in the media, and he interviewed lots of people from Alcoa. Most of the books that are written about companies are written by the companies. They're paid for by the companies, so they're sort of biased. Okay, this guy actually goes through and he says a lot of things. I showed you the picture of the nice, beautiful Pittsburgh Reduction Company, and then the real picture. You know, Alcoa wouldn't have put that in if they had paid for the book, right? But anyway, so right after, on the eve of World War II, not after World War II, Alcoa had a monopoly in bauxite, which is the raw material for the hull cell, and alumina, which is an even purer material. And making real aluminum, pure aluminum, Alcoa owned the business in the United States. Okay, they were the only ones in the business. Fabricated aluminum products, they owned 50% on average. Foil was only 50%. Who was the other big foil producer in aluminum? Reynolds. And why did Reynolds go into the foil business? Reynolds is part of Reynolds Tobacco, or was part of Reynolds Tobacco, the Reynolds family of Richmond, Virginia. And they needed something to wrap their cigarettes in. And they decided, we use enough foil, we might as well start our own aluminum foil business. And so Reynolds Aluminum is a spin-off of Reynolds Tobacco. And so that's why Alcoa didn't have, or only had 50%. It turns out the only three aluminum companies of note were Alcoa, Kaiser, and Reynolds. And Reynolds was very specialized at that time. They've grown in what they do. But anyway, Alcoa was a pretty well integrated monopoly. Remember, there were other integrated monopolies. Henry Ford, making automobiles, he had his own steel plant. You know, he had his own glass plant. You know, Alcoa had their own hydroelectric plants. They built big dams. There's a town, anybody from Eastern Tennessee? A town right near Knoxville called Alcoa. You fly into the airport for Knoxville, you'll be flying into Alcoa, Tennessee. Alcoa built hydroelectric plants in the Smoky Mountains back in, they started out at Niagara Falls because that's where you get your electricity back in the 1890s. But by 1910, they were going to other places where they had wild rivers and building dams and building big smelting plants, wholesale plants. In fact, Alcoa still has a plant in Alcoa, Tennessee. Okay, that brings us up time to start class. So that's just another little thing. Any questions from people who just showed up? No? No? Okay. The schedule is Dr. Belmar will do Friday and Tuesday. Monday's a holiday. We'll start presentations on Wednesday and Thursday. Turns out the reason I wanted to get things started is because things come up, and it looks like next Friday I've got to be in Houston. So the people who are listed here for Friday, and I'll have Jerry send this around. We still have some people to sign up, okay? It looks like we are going to run into November 3rd if I have to cancel next Friday presentations, but hopefully I won't have to cancel too many of these. All the other days on here are good. I didn't put down the 30th and 31st because I have to be in Houston on those days. In any case, that's the schedule. We handed this out, so most people should have an idea of what the schedule is. Okay. Any questions or any the other new people that just showed up? Nope. Okay. The themes from Tuesday: the brittleness of glass, which makes it unfit as a structural material in general, okay, is overcome by surface modification. You can encapsulate, that's called fiberglass. You can use thermal processes, that's called tempered glass. You can use chemical processes, that's called ion exchange, where you substitute the sodium atoms with potassium atoms, or if you really want to get a lot, you can make a lithiated glass and substitute it with potassium, and you get a even bigger difference. So glass is a structural material. So all the things I tell you, and most things, I often say, whatever the rule is, there's usually exceptions to the rule. And so if I tell you the rule is you need fracture toughness to be a structural material. That's absolutely true, and that's an important thing. But it turns out glass has certain properties. It's transparent, and so we like that for certain applications. And there's not a lot of other choices other than plastic, which doesn't have a lot of strength. And I gave you some things comparing glass to plastics as structural materials. Glass also can give you fantastic strength. Those fibers, when they're freshly made, can give you 500,000 psi. I mean, if you test them within minutes of forming the fiber, you can get 2 million psi on glass fibers. But within hours, it's down to only 500,000. Well, that's still pretty good. It's just as good as Kevlar fiber, okay? And so you can make fiberglass, and we make boats out of fiberglass, and we've been doing it for years because glass has very good strength, has terrible toughness, but we can get around that. You get the toughness by basically making a composite. And you can do thermal treatments to temper the glass so that it doesn't shatter with terrible shards that are going to kill people. And you can do chemical tempering if you really want to spend some money. This is a process that takes a couple of minutes. This is a process that takes hours, like 3 or 4 hours. So obviously chemical tempered glass is not used as often. It's pricier, but it gives you a much thicker layer of protection. We were talking the other day about how deep the compressive stresses go, okay, from the surface. And the chemical tempering gives you excellent properties, maybe 40 or 50 microns. And thermal depends on the thickness of the glass. And it can also be a few microns as well. But you've basically got to get rid of those scratches on the glass that go, you know, 1/10 of a micron deep. Those are harmful. Okay, so that's glass. And now, since it's the last day, I've got to cover the rest of the periodic table, okay, of structural materials. Now we've done aluminum and we've done most of the aluminum. The other theme from the other day is aluminum was monopoly from 1890 to 1945. I told you that one of the Achilles heels of steel is corrosion, okay? Steel rust, and we do all kinds of things to protect against that. We came up, or the Swedes in Sweden around 1907 or so, they added chromium to steel at more than 10%, and they came up with stainless steel, and we use a significant amount of stainless steel. About 2 to 5% of a typical steel industry is going to be in stainless, okay? So in the United States, we might use, if we use 100 million tons of steel a year, we might use between 2 and 5 million tons of stainless. There are 5 different types of general types of classes: ferritic, martensitic, austenitic, duplex, and precipitation hardening. The big one is austenitic. That's 304 or 18-8 stainless steel, and there's a whole genealogy chart of this. We don't have time to go through all of these. I think in last year's lecture I finished up a little bit earlier, and I spent some time on this. And here it says stainless steel is about 2% of all steels. But there are problems with stainless steels in that my experience is, although stainless steels are 2% of all steels, which makes them about 2% of all metals, they constitute 30% of all the problems and failures. That's because everybody figures, oh, well, it's stainless. Well, a lot of people, you read some things and they say, it's stainless, it's not stain-free, okay? I mean, people bring me about once or twice a year, someone will bring me a piece of something, they say, this was supposed to be stainless steel, it's all rusty, so it can't be stainless. Someone gave me the wrong material. I said, no, that's stainless. You get rid of that protective chromium oxide skin and it will rust, okay, just like regular steel. So, now aluminum, which I haven't finished up here completely, but it's the second most widely used metal, 2% of steel, about 20 million tons a year, but it's 5 times the cost of steel, okay? Historically, we've gone through as more precious than gold, and a significant fraction, like it used to be, it may not be quite this anymore, but aluminum was 40%. 40% of all aluminum went into can stock, beverage containers. That's a sweet spot for the aluminum industry. There's a lot of different alloy series. If you take some of the other things on the web, other modules, then I end up going through some of these things. There are heat treatable and wrought steels. The wrought steels are basically things like the 3000 series, which is can stock, and the 5000 series, which is aluminum magnesium alloys. It's not heat treatable, but you can weld it and get essentially full strength. So if you're the U.S. Navy and you're trying to build an aluminum ship that's lightweight, you're going to have to weld it so you make it out of 5000 series. The aerospace industry likes to use heat treatable because they're going to rivet it, they don't have to weld it, and instead of getting 25 KSI, or 30, which you might get in the wrought material, although they've got some wrought materials up in the 40 KSI that are a little bit stronger than the lowest strength steels, you can get 75 KSI. And in fact, the problem with the heat treatable, they actually can start to degrade at fairly low temperatures. The supersonic transport Concorde was not limited on speed, it was limited on skin temperature of the heat treatable aluminum alloys. They would start to overage and you'd lose your precipitation hardening. So they actually had sensors on the surface that would measure the temperature. And the colder it was up there, okay, at whatever altitude you were, the faster you could go, okay? But it was limited. You didn't want to destroy your aircraft by overheating the aluminum. So, and that's the same type of thing. They've just started coming out with aluminum in automotive brakes. But the first real problem of aluminum, trying to use it for calipers and disc brakes and things like that, not the drum, but the caliper that holds the brake pads. The first big problem was they would creep. You hit your brakes hard, and you get too much temperature, and all of a sudden the caliper holding the brake pad starts to splay out, and you no longer have any pressure on your brakes. And your brakes, it's called brake fade, and it's not a good thing. Well, they fixed some of that, yeah.
I was wondering, so you said the Concorde, it was like the friction, like air friction?
Yeah, just, yeah, air friction on the skin at 40,000 feet. Okay. Now you start getting up to 60 and 70,000 feet where the spy planes go, they actually had to use titanium because they couldn't use aluminum. The frictional, don't ask me why. I'm not sure I understand why. You get more rarefied, you get more friction. Did you know, Sam? Oh yeah, exactly. Yeah, you get the shockwave effect. Yeah, you're right. I mean, they're going, the spy planes were going supersonic and the Concorde, well, the Concorde was going supersonic, but yes, it's more friction because it's supersonic than a Boeing 747. A Boeing 747 doesn't have to worry about the skin temperature. It's minus 40 up there, okay? It's when you go supersonic. But the Concorde was supersonic. Why the spy planes, maybe they were going Mach 4 rather than Mach 3 or Mach 2. Actually, I think the Concorde was about Mach 2 or Mach 2.5. I only flew it once. I did fly it once though. Anyway, so there are some issues, but in fact, all these things I've told you about how wonderful steel is, and I'll continue to tell you how it dominates the market. Here is something that you should actually write this down. Here is the Federal Aviation Administration Metallic Materials Properties Development and Standardization, MMPDS-05. It's about 11 or 12 volume set, about that thick. If you want to buy it, it's $110 because the government can't make a profit. It's the cost of printing it. If you want to download it, it's free. Okay? This used to be known as Mill Handbook 5. It was put together by the Federal Aviation Administration and the Department of Defense, but it's sort of been taken over because the Department of Defense is trying to get out of the standards business. This document it replaces anyway Mill Handbook 5, okay, which was maintained by the U.S. Air Force. Okay, so that was up until 2004. The Defense Department is trying to get out of being the standards writing body for the country. So they turned this over to the Federal Aviation Administration. It was originally written in conjunction with them. Actually, it's a compilation. If you're the Defense Department and you got that kind of purchasing power, you can tell Boeing you want some data to go into this handbook. And Boeing wants to give it to you because the FAA is going to define the material properties that you can use to build your aircraft in terms of this handbook. In fact, that's what it says. This document contains design information on the strength properties of metallic materials elements for aircraft and aerospace vehicle structures. They have two different types of, or tolerances, and the aerospace, or the spacecraft tolerance is much narrower band of strength requirements. Regular grade, I think it's grade B, is a broader band, and that's for most regular aircraft. But, I was going to read you something from here. Oh, scope of the handbook. Handbook is primarily intended to provide a source of design, mechanical, and physical properties and joint allowable, so it takes care of welds. Material property and joint data obtained from tests by material and fastener producers. So they go out, and anybody that the Defense Department would buy from, they'd say, give us your data. We want to put it in the handbook. And you want to give it to us because what data we put in there, we're going to help evaluate. And this is what we're going to say is your design allowable. When you design an aircraft that you want FAA approval for, if it's commercial aircraft, or you want the military to approve, you must use the data in this book.
Why would they let them, isn't that sort of like self-regulatory? Because if they're providing the data, that determines.
Oh, but all the aluminum producers got to do it, okay? And then the Defense Department and the FAA will evaluate everybody's data, and if there's a big discrepancy, they'll say, okay, let's have a little meeting and work this out.
Right.
And the lowest quality might end up being the one that goes into the book, okay? Because, no, the government can't say, well, Alcoa, you've got a better grade of 7075 aluminum, and therefore we're going to require everyone to buy your better grade. The government actually has to go to the lowest common denominator on properties, okay? So, no, they got some regulations they have to worry about. This is just the introduction, which doesn't have, well, it's just an introduction. But if you go to, well, if you go to one of the books, this is chapter 2. This is the whole book on steels. And why do steels come first? Hey, I told you why steels come first. And this is just a wonderful book. Graph after graph. It's nothing but graphs of data. This is why you want to have a copy, because it's free. And it's materials, okay? And hey, it's not a bad source to look up data. But remember I told you steel was more important economically than as an industry than aluminum? 2 volumes on aluminum, 1 volume on steel. And the 2 aluminum volumes are thicker. Why? You make aircraft out of aluminum, not out of steel. Why? Because steel's heavy. Another one of its problems. So guess what? If you're writing a design manual for aircraft, aluminum's going to be the big gun. Okay? Not steel. So steel doesn't always win. Okay, it loses in corrosion and some other things. Here's magnesium, cute little thing, isn't it? Okay. Heat-resistant alloys, nickel-based superalloys. All your engine materials, not too thick. Believe me, there's a lot more data out on this stuff that is proprietary. And titanium alloys, it's less than steel, okay? But there's a fair amount on titanium compared to its market volume, because titanium tends to be used in aircraft, okay? So it's worth thinking about whether you want to fill up your computer space with that, okay? Well, if you're going to be in materials, you ought to at least know about it, okay? Okay, other materials. If you went back and looked at, I gave you a plot. If this is the last lecture, this is what we did in the first lecture, where we said structural materials production, and this may not be the exact graph that I gave you, but steel is 1.5 billion tons, aluminum is 45 million tons, copper is 15 million, zinc is 12 million, and you can go down to these other non-metals, and at least cement and stone are larger than steel. Plastics, as a whole, all plastics are more than aluminum, but they're nowhere close to the amount of weight of steel, so far as that goes. And we're going to talk a little bit about why these are where they are. Okay? Copper has some unique properties. One is got color. Yeah, but that's not why we use it most times. Although sometimes for architectural reasons. What's the number one property of copper that we really like? Conductivity. Which type of conductivity? Both. That's right. Very good. So if I want to look at, if I take the train from Amtrak from Boston to New York, I'm going to be the electrical conductors, that's an electrical train, is going to have trolley wire. You go look up and they got all these ugly towers the whole distance. And this is about a 0.545 inch diameter, and it's got a cross section so you can clamp it like this. And the graphite brushes that are on the top of the train will slide along this thing at 100 miles an hour, right? So that's trolley wire. They wanted to make it out of an aluminum ingot that looked like this. I have this stuff because one year on December 22nd, I got a phone call saying, you have to tell us by Christmas, 3 days later, whether we can accept $6 million of this material to go for the New Haven to Boston extension.
This is how thick it is?
And, huh?
This is how thick it is?
Well, that is a wire. Yeah, that's all that carries. And it's because it has good electrical conductivity and good corrosion resistance on the surface, better than aluminum, okay? But you want electrical conductivity, and you're willing to pay a premium. So I had all of about 48 hours to figure out whether to accept or reject this. I rejected it. And they had to go buy some material from a different supplier. It's probably, the story is probably in one of my other lectures. But in any case, the grain size was too large, okay? Because it was too pure, turns out. And they needed to get some strength, so that copper alloy has 0.2% silver in it to strengthen it. That makes it even a little pricier, okay? But pure copper is very weak, okay? It also has very good thermal conductivity. So I've got a piece here. This is a piece for thermal conductivity. And this is actually a tensile specimen between molybdenum and copper. And they did a transient liquid phase diffusion bond. I'm sure I talk about this in one of my other ones, certainly my joining. Molybdenum will take very high temperatures. And so if you have a radar system, and you want to have amplified radar if you're trying to do fly, if you're the military and trying to fly nap of the earth at sonic velocities, okay, but a couple of hundred meters above the surface of the earth. So if you make a mistake, you don't have time to make a correction. You have to rely on your radar to keep you from running into a hill, okay. They have some very powerful X-ray machines, and they do that with an electron beam that generates the X-rays, or the radar amplifier, and you would melt copper with the heat intensity of that pulsed electron beam. But you won't melt molybdenum, but you need the thermal conductivity of copper, so they make a composite. They braze a little, about 2 millimeters of molybdenum on the end of a copper piece. The molybdenum takes the heat, and the copper carries it away. Yep.
What's this striation in the middle?
Oh, that's what we call orange peel. Those are the grains in the copper. When we did the tensile test, you're starting to see it deform in the crystal structures because you have slip on different crystallographic planes. That was a smooth bar when it was machined. But when you start deforming it, each one of the grains deforms at a different rate, and you end up with what they call orange peel because it has the kind of texture of an orange peel.
It's not unique to copper only, right?
No, it's not unique to copper. We see it more in copper alloys, but it shows up, I've seen aluminum with orange peel. Okay, you got to start with the incorrect grain structure to begin with, and copper tends to give you that. Okay, you can get orange peel in steels, okay, but we know how to produce fine grained steels that won't give you that. Okay, very pure coppers will give you large grain size, just like the casting that is going around. Okay, the purer the metal, the easier for the grains to grow. Okay, impurities are one of the best ways to suppress grain growth up to a certain extent. Okay, so copper has unique electrical and thermal conductivity, and even though it's much more expensive than aluminum and steel, we use it. Okay, now we don't use it. Aluminum has 60% of the conductivity of copper, and so all those big 345 kilovolt transmission towers and stuff, that's aluminum, because you don't want to pay that much for the copper, okay? However, the aluminum tends to get soft, right? So you actually make a composite. Those are actually steel cores with aluminum on the outside. And the steel gives you the strength. And one of the reasons for that is, why are they so tall? Well, one of the reasons they're so tall is when you have, everybody's running their air conditioners during the summer, they heat up. And they actually have to make them tall enough so that as it heats up and expands, it doesn't touch the ground. Because if it touches the ground, it will start a forest fire or a brush fire. Plus, it's not very good for the circuit breakers back at the power station. You'll lose your power. And remember, I don't know if you would remember, you might remember, it was 7 or 8 years ago they had some tremendous wildfires in San Diego. And it would just burn down all that part of Southern California. Well, it turns out some people finally got a big $300 or $400 million lawsuit, or got a settlement out of the utility, because they claimed that their wires, when during the summer everybody's using the air conditioner, they came and they touched the ground and started a fire that burned down most of Southern California. Whether that's true or not is another question, but the threat of the lawsuit caused the utilities. And why would the utility pay hundreds of millions of dollars? We sort of discussed this before. Didn't I talk about putting things onto the rate base? The rate base. If they have an expense and they can justify it to the regulators in the state of California or Massachusetts, if it's Massachusetts, they just pass the cost on to the consumer. So why not pay off the attorneys? Why do you need that hassle and all the bad press and going to court and everything else? Let's give them hundreds of millions of dollars and then put it on the rate base, let everyone else pay extra $10 a month on their electric bill. Okay? So all those people in California, look at the battle they won. They now have higher monthly electric bills for the next 10 years. Okay? These are one of the externalities, okay, that we talked about before. So titanium and tantalum have outstanding corrosion resistance. We know that. In fact, that's one of the reasons why titanium's here at 165,000 tons. Half of that, or maybe more, is because of its corrosion resistance. Not because it's lightweight, high-temperature structural material, which it is. About half of that goes into the aerospace industry, and the other half goes into the corrosion resistance industry. Okay? Making tubing for heat exchangers and all kinds of things. So, and yeah, it's in the medical business. I think I have a little stent here. Here it is. I'll pass it around. It's a little welded titanium wire. Okay, here. It's a little welded titanium wire. So they put this. They'll fold this thing up, slip it in a tube, bring it in right next to your heart, open it up, let the spring open, and it will catch all those clots that are going to kill you. Okay, just a filter. Okay, but it won't corrode in the human body. You try to make that out of stainless steel, it'll be toast in a year. Okay. Yeah. Look, check out your aorta and figure out how big it is. Okay, and it's got those little hooks on the end. That's what digs into the wall of the artery. Now this is an old one from like 10 or 15 years ago. Nowadays I'm sure they're more sophisticated, but they had some problem on the welding of the tip there, so I don't know. It came to me, I don't even remember what the problem was, but in any case. So titanium is great for the human body. Tantalum is even better. But in most of these things, we get down to cost as one of the big drivers. Anybody have any, I mean, this is a very general kind of wrap-up lecture. If I go to, I've shown you this type of thing before, the periodic table, and I say, well, what elements do I use for structural materials? I use almost all the elements on the periodic table for something. Even technetium, which doesn't exist on Earth, not as a structural material, but I do use it in radiology for people who are getting stress tests in a hospital. Even though it's only got a half-life of 10 hours, They make it, they fly it in Learjets around the country, and when I had a stress test at Mount Auburn Hospital, they shot me full of technetium, and then I was radiating fast enough they could take pictures of my heart pumping while I was running on a treadmill. How exciting, okay? And they learned I'm out of shape. Okay, fine. Okay. So even technetium, which doesn't exist on Earth, we use. We don't use francium because francium is never really, it's also radioactive and doesn't really have much of a, well, don't have a use for it. If we could find a use, we probably would make it, like we do with technetium. And of course, all the transuranics are used for, like plutonium, which is made in tonnage quantities. Most of these are not used except for plutonium. Americium is used. Americium, right? Americium is the way you pronounce it. Anybody know what it's used for? Smoke detectors, exactly. It's a little radioactive source that helps ionize the particles that will set up enough conductivity in the air to tell you got smoke in your atmosphere. And it will set off the alarm and wake you up in the middle of the night. Or while you're fixing dinner and creating your own smoke particles. Okay. It just, I mean, now you're going to have to ask the nuclear engineer. It gives off the right energy, probably beta electron particles. It could be alpha, I don't know. I don't know if it's a beta emitter or an alpha. Alpha emitter is a helium nucleus. Beta emitter is an electron. And in the radioactive decay, it has the right properties to ionize the air, okay? And so they have a very little piece of radioactive material in there. But it happens to be americium for its nuclear properties, but I'm not a nuclear engineer, so I can't answer you, but we don't have any nukes in here right now, right? Anyway. Okay. Well, we don't, these things, cerium is used in ceramics. Cerium oxide has some interesting properties. All the rest of these are used in functional materials, okay? Except for neodymium is used in neodymium iron boron magnets. Promethium is also like technetium, doesn't really exist in any large quantities. But what was I going to say about? I don't remember what I was going to go to the board. Anyway, oh, there's structural materials and there's functional materials. Is what I was going to write down. Okay, now, and I covered this one of the early days, maybe not the first day. Okay, structural materials versus functional. I guess what the message I want to give you right now, the theme for the rest of this morning is there are very limited numbers of structural materials we really use. We use almost everything else for some functionality, like americium. That's not a structural use. It's because it has certain nuclear decay properties that are good for ionizing particles in air. Okay, most of these others we don't really use in large quantities for structural materials. I mean, carbon and silicon are the basis of lots of polymers, silicones and hydrocarbons. Aluminum and silicon and magnesium and calcium are used in stone and cement. The metal, aluminum, copper, iron, if you went back to my list, those are the top three, okay? In use volume, aluminum, copper, okay, then you get down to zinc. What are the major uses of zinc?
Galvanization.
Galvanizing. So zinc is mostly used to protect steel, okay? I'll bet 80% of that 12 million tons of steel, of zinc, goes into protecting steel from its problem of corrosion. There are zinc alloys, we call them pot metal castings. It used to be the handles on cars back 30, 40 years ago were a zinc die casting. And you go to the hardware store, you can find these little cheap metal parts where you want a metal part rather than a plastic part. And it's a metal part's stiffer and whatnot, but they're zinc die castings. They don't have a lot of strength, but they're cheap to make. You can make them by die casting, and they're just as cheap as popping out plastic parts, but they're stiffer and stronger. And so when you need a little bit more than you can get with plastics, or you need a little more temperature, not much more temperature, you can use zinc. But most of the zinc is going to be used to protect steel. So I could do this for a lot of things, but zinc basically comes over here And its major reason we produce zinc is because of the steel industry. It's also used in some aluminum alloys. It's used in some of the gold alloys and things. But anyway, if I start looking at the periodic table, I can wipe out as structural materials the whole first column. I mean, lithium is obviously very important for batteries. Sodium is used in glasses as an alloying element with alumina and silica, okay, and magnesia and calcium. But these things, well, what's one of the problems here? In the presence of moisture, what happens to these things if they're metallic?
You get hydroxide.
You get a hydroxide and what is left over from the water molecule called hydrogen. I mean, you ever seen anybody drop sodium on water in high school chemistry and you get a little fire dancing around the water, on the surface of the water? Okay, so they don't have very good corrosion resistance as metals. They might be used as oxides and chlorides, and they have some fantastic functional material properties as optical materials, as sodium chloride or potassium fluoride or whatever. But as structural materials, they just don't cut it at all because of their lack of corrosion resistance in the atmosphere. Even humidity will do it. Beryllium is sort of interesting because it's very light. Actually, it has the same density as magnesium. It's actually very slightly more dense than magnesium. But it has very good high temperature capabilities, but it's extremely expensive because of its toxicity. Any type of beryllium, if you are 10% of the population and you have a genetic predisposition to have your lungs react with beryllium, it's only 10% of the population. But any beryllium compound that gets in your lung, whether it's metallic beryllium or beryllium oxide, or beryllium chloride, anything, so far as I know, that's beryllium compound, will grow these nodules in your lungs and you will slowly suffocate. And this was all discovered up here on the corner of Mass Ave and Vassar, okay? During the Manhattan Project in World War II, they had a machine shop there. Right now, it's a Bank of America kiosk and stuff. At least I'm pretty sure this is where it was. They had a building there, and guys were machining beryllium alloys, which were sort of new because remember, the mechanical engineering department came up with this way to vacuum melt metals, and they were able to make beryllium alloys, which are very light, and they had some uses for them in the nuclear weapons. And so they were machining things experimentally here at MIT. And some of these guys in 1944 and 45 started coming down with these health problems. And they ended up contaminating the whole building. I've heard the story, I've never confirmed it. They actually, eventually just sat there for about 10 or 12 years. My thesis advisor told me some of this because he was an undergraduate here in the mid-50s when it was sort of sitting there. And they eventually encased it in concrete and carried it and dropped it in the Boston Harbor. Yeah. Yes, you had a question?
Oh, what do you mean by nodules exactly? Like,
You just start growing little cysts, around your body's trying to encapsulate the beryllium, okay? It doesn't like beryllium. And so your body will start reacting and creating little lumps inside your lungs. So anyway, it is toxic, okay? So, but we do use it. Yeah, but it's only about, well, they didn't know that originally, but now that we can do genetics and DNA tests, some people have it's only about 10% of the population. If you go to Kawecki Brill Co. and look on their website, and they have something that talks about berylliosis, it will tell you that only about 10% of the people will get it, okay? Unless you want to, if you have a test, you probably find out whether you're susceptible. But nonetheless, everybody's afraid of beryllium. When I was department head, had a young assistant professor who actually became Chris Hughes' thesis advisor at Northwestern, and we were cleaning out Nick Grant's old lab, or he was cleaning it out on the third floor of Building 8, and he found a little plastic bottle that said BE on it, and he came rushing into my office. I found powdered beryllium. And so I said, well, okay. And so we went over there and I picked it up. Oh, you touched it. You touched the bottle. I said, I'm just talking, David, I'm not drinking it. Okay? I'm not breathing it. It's just in the bottle. I'm picking out the bottle. He saw BE on the bottle and he thought that he just come across a nuclear weapon. Okay? anyway, so we had to call Environmental Health Services, and they got to dispose of it. I'm sure Nick Grant probably had that since 1945 or whatever, and it had been sitting in the cabinet, and when he finally retired, we were clearing out the cabinet. There's a lot of other interesting things in there too, but anyway, I had to calm down the assistant professor. I already told you about beryllium tools, and I can take copper and beryllium and I can make something as hardened steel, 180 KSI, okay? So I can make tools that don't spark because it has a very good thermal conductivity of copper. And beryllium's the only thing that on the periodic table that can do that to copper, okay? If we had anything else, you think we'd be using beryllium at the price of beryllium? But beryllium's unique in those properties. So beryllium's sort of interesting. Scandium, yttrium, and lanthanum. Well, they're all interesting for ceramics, for functional materials. The only use I know of any of them as well, and some of the ceramics, like yttria stabilized zirconia ceramic, can be a structural material. Scandium does go into metals. If you look at my little chart, I had scandium on here at 2,000 tons a year. Okay, SC scandium down here. Anybody know what scandium is used for in alloying? Aluminum, right. Anybody know what the highest strength aluminum alloys are? And they're not used for aerospace. Ta-da! 100 KSI strength. Because if you want to hit home runs, you need to match the stiffness of the bat to the stiffness of the baseball or the softball. And to do that, since the aluminum's got this high modulus and the cork and, you know, twine and everything else, and the horsehide has a low modulus, the way to do that, this is solid, this has to be very thin wall so you get the springiness of a trampoline effect. In fact, they call it the trampoline effect. And you know, actually, one of you was talking about you doing, was it lacrosse rackets, or anyway, you're doing some sports thing. Well, you said pole vaulting, no, but someone else, maybe she's not here. She had some sport and she wanted to do, she was interested in I think it was lacrosse or something. Anyway, composite materials for whatever. Oh, and they're now going to composite baseball bats, she tells me. A couple of years ago when I was looking at this, they were still mostly aluminum. You can dial in the properties, but the way they get 100 KSI, they add scandium. Scandium alloy, it says right there. Okay? What does that mean to most of the little leaguers? Not much. Scandium alloy? They don't even know what an alloy is, much less scandium. But scandium can give you extremely fine grain size. That's extruded as a tube, and as you extrude it, you're quenching it at the same time. So you do your heat treatment process as part of your extrusion. So it's just like squirting out toothpaste, but you can get tremendously fine grain size and tremendously rapid heating and cooling, and therefore you can get 100 KSI strengths. Alcoa has made a number of proprietary alloys. Well, they're not really proprietary. A number of specialty alloys that they sell to the baseball bat manufacturers. It's a huge industry. I had no idea how big that industry was. But they're up to about 105 KSI now. But they're getting so thin in the wall that some of these things you can take about one good hit before you start getting cracks in your bat. Who wants to pay $150 for a bat and then use it once, right?
Question, for the copper cables for the trolleys and trams,
Yep.
you mentioned that they also introduce silver impurities sometimes to suppress grain growth. Is that like
Yeah, and to add strength.
right, to
Okay.
add strength.
Yep.
And is this the same situation? What's the mechanism by which
This actually helps with the precipitation hardening and the grain size. You can use titanium, but it's not as good. The Soviets really developed the scandium edition, okay? And if you really want to get the best, and only the baseball bat, you know, actually sports materials actually often leads in a lot of other things, because as I always say, you can sell anything to a golfer, okay? You know, high end of their earning capacity, you know, old men, okay, who want to be able to brag against their, you know, the other CEOs on the golf course that they, you know, anyway. So they'll pay anything. They'll pay $10,000 for something that it's hardly worth it. Anyway. It's all pride, yes.
Isn't that like the first application of metallic glass?
Yes, they were making metallic woods or, you know, golf heads. And they would get about 6 shots before they would all crack and everything, okay?
Sorry, so what is the mechanism by which an impurity suppresses grain growth?
It goes to the grain boundaries and it gives grain boundary drag. I mean, if you don't have impurities, the grains will grow by diffusional mechanism. If you have impurities there, you get what's called grain boundary drag.
Oh, where it literally gets caught on the...
Yeah, you want something that actually is surface active on the grain boundaries, and it gets caught, okay? It's sort of like precipitation. Precipitates will do the same thing, but even individual atoms will do it too. It's called grain boundary drag. Now, titanium, zirconium, and hafnium. Well, titanium we already know about. Zirconium is a structural material in a very special application. Anybody know what? This is crystal bar zirconium. You can tell it's fairly heavy. It's made by reducing zirconium tetrachloride on a hot wire of zirconium, and it just grows from the vapor phase. This is a zircaloy alloy tube, nuclear reactor fuel cladding. Very low nuclear cross section. Those little neutrons go right through it, okay? And so it won't poison the reaction. Okay, if you know anything about nuclear reactors, one of the ways you poison the reactor is you put boron in there. You have borated water. Boron absorbs neutrons like gangbusters, and so you can poison the reaction and shut it down. So if you have something like 3 Mile Island, you want to dump borated water on top of the reaction to poison it and stop it. Hafnium, on the other, or zirconium, has very low nuclear cross-section, which means it's transparent to neutrons. It has to be very, very pure because a little bit of hafnium impurity in the hafnium poisons it and it starts absorbing neutrons at a very low concentration. Vanadium, I only know of one vanadium alloy used in very specialized oil field application for corrosion resistance. Niobium and vanadium, their major use, where they make 1 million tons, well, I don't know, 1 million tons, but hundreds of thousands of tons, I haven't got them on here. It's because they're alloying elements in steel. In fact, what I'm going to tell you is most of these other things on the periodic table, we use them just like zinc because they're alloying elements in steel. I got 1.5 billion tons of steel, and if I only put 1% nickel in all that steel, I would use more than all the nickel in the world. Okay? And we do like nickel and steel. We'd love to have nickel and steel. It's too expensive to put very much of it in. Cobalt is even more expensive than nickel, but it makes good high temperature alloys. Nickel is the base of all our super alloys in general. Manganese, about the only thing we use it for. We have huge blast furnaces, turn out 500,000 tons of manganese a year because most steels have about 1% manganese in them. That's, 1.5 billion tons. That means 15 million tons of manganese a year. Here's a manganese C nodule, okay? So back, I was going to explain that. Back around 1975, some of the companies like Kennecott Copper, I think, was big on this. And in the Atlantic Ocean, near the Middle Ridge, if you go down about 6,000 feet, you will find floors loaded with billions of tons of that. And it's extremely rich in copper, which is why Kennecott Copper was interested in it. If you want to see a cross-section, if you go to the Infinite Corridor, you'll see a little nickel and copper. It has lots of nickel and copper, but it's mostly manganese. And you could throw that straight into a furnace and start refining the metal, okay? The only problem is they're 6,000 feet deep, okay? But they were looking at mining it in the 70s because they're just scattered all over the seabed, and they got some in California, off the coast of California. And so I got that from Professor Clark, who got it at some open house at MIT in the mid-70s. But Nick Grant at the time, who was now alloy developer here, he wanted to start a whole manganese metallurgy, just like steel, iron, which manganese economically could compete if you had rich ores like that, and they weren't so difficult to get, being at the bottom of the ocean. But if you had ores as rich as some of our iron ores for manganese, manganese economically is made by the same process of making steel. Put carbon in a blast furnace with manganese oxide and you get manganese metal out, manganese carbide, or manganese and carbon alloy out. Just like you do with making cast iron, yes.
Where did those nodules come from? Like, where
They were formed by some geological process, you know, these vents in the middle of the North Atlantic Ridge and stuff.
are they even attached to something? Or are they
Nope, they're just sitting there on the bottom. I mean, I don't know exactly, but I assume that you have spewing up, you know, minerals into the water from the vents, and somehow they're nucleating and growing, and you know, sort of like hail coming down falling on the surface of the ocean. But it's kind of deep, and if it weren't so deep, if you could drain the ocean, you'd have an excellent source of ore.
Isn't manganese also used in an aluminum alloy called duralumin?
Yeah, manganese. Well, all the 3000 series aluminum alloys are aluminum manganese alloys. Can stock, 1% manganese. So manganese but it's used as an alloying element. One of the reasons is you got to start looking at manganese. Manganese is allotropic like iron. Iron has alpha and gamma, BCC and FCC. Manganese is almost as bad as plutonium. They got like 5 or 6 different crystal structures. And so talk about complex metallurgy, okay? This thing's transforming in all kinds of ways, and when you start alloying with it, you get rid of one phase and start another phase. It's just a mess, okay? Very few people really publish in the open literature on plutonium, but I mean, there's been a lot of good metallurgy done on plutonium. It's just not very public, okay? Anyway, most of the rest of these, cobalt and nickel, they tend to be alloying elements and other things. These are the light metals over here, okay? Cadmium, indium, okay? They melt, mercury, melt at low temperatures. Here are your precious metals. One of the only precious metals we use in fairly high volume is turbine blades. This is actually for growth of a single crystal turbine blade. That's 6% rhenium. I don't remember, rhenium's about $40 an ounce or something. And for the turbine blades and the engines that you fly in the airplanes, that alloy, in order to get high temperature properties, has got some rhenium. They'd love to use platinum, but it's kind of pricey, a lot pricier than rhenium. Rhenium's getting over here on the periodic table close to the tungsten and molybdenum. Silver and gold are mostly used in jewelry and pride metals, okay? Palladium and platinum are used as catalysts. That's functional material. Rhodium is used as a catalyst. Iridium is used as a catalyst. You start looking at the periodic table. These are not structural. These are gases. These are low melting. These are mostly alloying elements with iron or copper or aluminum. These are useless as structural materials. These can only be used in an oxidized state, like a chloride or an oxide usually. You can use them, but they got corrosion properties just like these others do. Anyway, you start looking at the periodic table. We don't have a lot of choices. And when you add economics on top of it, we really only have a handful or 2 handfuls of choices, okay? Which most people don't realize. And they're always hearing about the functional properties of these other. Oh, we used erbium to make a beautiful red color phosphor in one of our display screens or something. Okay, fine. And you'll sell a couple of pounds of that a year, okay? Because you're using it in parts per million quantities, right? Talking structural materials, we're talking very large volumes. Tons, millions of tons of material. And there are just not very many choices. Okay? Okay, if you have questions about your presentations and stuff, you can come see me. I will be around every day but Friday of next week. And I'll be here tomorrow and stuff. Okay? Thanks. And don't forget to watch your other module at some point.